Yuichi has been working in our lab for the last 5 years, and he's been absolutely fantastic at doing new work on humanoid locomotion. We started this project, with a pretty narrow goal, I think, which was just to make a pretty decent footstep planner for a humanoid robot. That was kind of our goal at the beginning. And Yuichi just took this and ran with it. First of all, he found footstep planning in the old style was way too easy. So we started focusing on planning with hand contacts and then planning in very large unstructured environments using different modes of using feet and hands. And then that still wasn't enough for Yuichi. It was too easy for him. So he decided he's going to start looking at how to plan contact sequences that account for the dynamics of the robot, which had, to our knowledge, never been really done efficiently. So he solved that problem, and that was still not enough. So he went on and he, in his most recent work, looked at planning with robustness to disturbances. So it's been a huge amount of work that he's accomplished, and some really great results and some really innovative algorithms. So, Yuichi, take it away.
So yeah, my topic is about learning for humanoid multi-contact navigation planning, and my name is Yuichi Lin. And as you may know that this thesis is about navigation planning for humanoid robots, and I would like to talk about why we need humanoid robots in the first place. And as you may know, that humanoid robots are notoriously difficult to control and maintain. And however, it does provide several benefits. First of all, it navigates by making and breaking contacts, which makes it capable of moving in unstructured environments without the need for a continuous contact surface, such as uneven terrains or places having gaps or obstacles on the floor. Some may argue that quadruped can also work in those environments. However, compared to quadruped robots, humanoid robot in general occupies smaller area on the floor and makes it easier to navigate in narrow spaces, and it is designed to adapt to human living environments and do tasks which is performed by a human now. Therefore, the community is still developing more capable humanoid robots and pushing its limit forward. And in this thesis and presentation, we will focus on motion planning of humanoid robots. However, directly planning in configuration space of the humanoid robot is very difficult. The first reason is its high dimensionality, which makes it expensive to plan motions in configuration space. Furthermore, humanoid robots stand and maintain balance by making contacts to the environment. Each feasible stance of a humanoid robot is in a lower dimensional manifold of the whole configuration space. Therefore, unlike many robotic systems, any two samples in the configuration space of a humanoid robot cannot be simply connected by a straight line or a parameterized polynomial. The robot has to follow a certain contact transition sequences to move from one configuration to the other. Therefore, we follow a widely adopted approach to decompose the problem into two parts. First, we plan the contact sequences in contact planning, and then we generate the robot trajectories to connect the planned contact sequences. And we will focus on the contact planning part and use existing approaches to generate the trajectory. And we target our application in unstructured environments, such as the disaster site you can see in the right here. And inspired by human motion in such difficult situation, we focus on contact planning using both foot and hand contacts to achieve more robust locomotion. Here we show this example in a right figure, and the planned contact sequence is marked with the colored rectangles. And turns out it's actually a much harder problem than only planning footsteps. First, more contact options becomes available, and which increases the branching factor of the planning problem and takes longer to find a solution. And since foot and hand contacts are in general not in the same plane, we cannot use popular simplified humanoid models such as inverted pendulum or support polygon. And this will take much longer to verify its balance and kinematic reachability and make the problem even more difficult to solve efficiently. And throughout the presentation and the thesis, we set up the problem in this form. Given the input of the start configuration and a goal region, and also the robot model and also environment model specified as a set of contactable surfaces. And we would like to run a contact planner and to find a contact sequence from start to goal using both foot and hand contacts. And we would like to follow the following constraints, including contact constraints, which means the robot has to make contact to the environment, and it has to be kinematically reachable since the set of contacts has to be reached by a robot configuration, and also has to remain in balance. And each contact should be also inclusion-free. And our objective is to reduce the total planning time to generate such contact sequence. And to simplify the balance check, we assume that the joint top limits are ignored. Okay, so in the history of contact planning, we can actually date back to the early 2000s when footstep planners were proposed to generate footstep sequence, just only foot, for humanoid robots to navigate through environments with varying terrain heights and obstacles. However, they mainly focused on environment with either flat or piecewise flat contacts and did not utilize the hand contacts for more robust locomotion. Therefore, the community starts to focus more on multi-contact motion planning, and it involves non-coplanar contact balance checking and also more contact options which increases dimensionality. So it is very challenging. Therefore, most works focus on environment with an obvious path to follow, like you can see here, and focus on generating a contact sequence around that obvious path. And in this presentation, I would like to use learning approaches to improve existing contact planners. So let's first talk about the challenges in solving the multi-contact, which means using both foot and hand contact, humanoid contact planning problem, and then how we will address each challenge. First, it is very time-consuming to plan contact sequences in large unstructured environments, especially ones with multiple selection of paths. And a conventional approach would select a shorter path and may get stuck easily if that path happened to be not easy to traverse. And to address this issue, we focus on how we can use learning to help select contacts in order to reduce planning time and avoid getting stuck. We first propose an approach which retrieves and adapts previous generated motion trajectory to fast generate contact sequences in difficult unstructured environments. And we then focus on large environments with multiple selection of paths. We train models to predict the robot's traversability in each region of the environment and use this information to guide the contact planning to search regions that are easy to traverse and thus reduce planning time and avoid getting stuck. In the second half of the presentation, we address the second challenge. A conventional contact planner does not actually consider robot dynamics and use the quasi-static balance constraints to reduce computation load. And it is actually an over-conservative criterion that may not be enough for challenging environments. And most conventional approach also only checks for feasibility and do not consider motion robustness. And in this line of research, we would like to train models to predict the robot dynamics in order to generate robust contact sequence efficiently. And we first explore contact planning considering dynamic motions and introduce a contact planner which verifies dynamic feasibility using neural networks to predict the robot dynamics for each contact transition. And continuing on this direction, we further consider the external disturbances and propose a contact planner which generates a contact sequence robust to such external disturbances. And to lay out the structure of presentation, I will first introduce a conventional search-based contact planner, and then we will move on to focus on our 4 contributions. And finally, we close the presentation with a conclusion. So let's get started. For planning from scratch, or PFS, or we call it PFS, we formulate the contact planning problem as an implicit graph search problem, and where each state or a node is a set of contact and effector poses, like I showing in the bottom left figure here, with the poses of the contacting end effectors. And an edge or an action is to switch one end effector poses as shown in this animation. And the neighbor function to generate the branching states are a predefined set of contact projections given the stance of the current state. For example, if you have a standing foot And this shows all possible moving foot you can project to the ground given by your standing foot, and also the possible hand projections given by your standing feet. And conventionally, the edge cost and heuristic are based on transition distance of the moving end effectors. And we would like to solve the contact planning problem with anytime non-parametric A star or NA star. And it will first be greedy on exploring states with lower heuristic. And the conventional heuristic will be like a distance from the current stance to the goal, for example. And once the solution is found, it then improves the solution over time to find paths with lower total path cost. And we show example run in the bottom right here, where the robot generates the both hand contact and foot contact to reach the goal. However, the performance of PFS drops when the contact spaces are limited. One reason is that the heuristic is agnostic to the constraints, including the balance constraints and kinematic retributive constraints. For example, a distance-based heuristic would suggest a large step, which may not always be feasible. And there will also be more rejections in contact projections to find branching contacts with a predefined transition model if the region is with limited contact spaces. So therefore, to address these issues, we would like to move on to our first contribution, where we use retrieve and adapt approaches to improve a PFS planner. So in retrieve and adapt, or we call it RA, we would like to avoid performing search over the graphs of stances. Instead, we would like to adapt existing motion plans to current environment and locally optimize the motion plan to fit the current environment. So given motion plan, a motion plan, or a set of motion plans, and this actually, a motion plan means a combination of the joint trajectories and also the associated contact sequence. And we'd like to store them to form a library of the trajectories and also contact sequences. And then when we face a new query environment, we will select promising motion plans from the library based on how close the contact poses are to how close the contact poses are for each motion plan to the surface in the environment. And then we adapt the motion plan trajectory locally with elastic strip-based trajectory optimization until a feasible trajectory is found. And here we briefly show an example of the RA approach evaluating existing motion plan. So in a given query environment, we first match with multiple candidates of the past generated motion plans. And once we find a promising one, and then we locally optimize it to form a feasible contact sequence and motion trajectory. And here we just play out the execution of the trajectory. Remember, this should be a quasi-static, so actually it should move a lot slower than what it shows here, but it actually shows the path the robot takes from start to the goal as a trajectory. And the key idea of RA is to avoid, or retrieve adapt, is to avoid searching contacts based on a fixed and potentially wrong heuristic. By following the assumption that contact sequences close to environment surfaces are more likely to succeed, RA tries to locally converge such contact sequence to be on the surface and within the surface boundaries. And that will avoid the discrete projections used in PFS, which may not find a valid projections in region with limited contact space. So to reinforce PFS, we set up RA to make it run in parallel to PFS. And for a given query environment, we will call PFS and RA in parallel, and whoever finished faster returns the solution. In this way, we can speed up the planning if RA can find a solution faster than PFS. And we verify if the contact sequence is feasible using a trajectory optimization approach in the end. So in experiment, we test in a bunch of randomly tilted surface corridors for different sizes of the library. So the environment examples, as you can see in the bottom here. And each trial is successful if a feasible motion plan can be generated within the 300 seconds time limit. And we run 100 trials for different orientation and tiltations of the corridor surfaces. So here, in the figure, we show that the result based on different library sizes. In the left, we show success rate, which means a motion plan can be generated within a time limit. So as you can see, only by using PFS, we have like a 35% of success rate. And by just using a very small array, it already a very small library size array, it already outperforms the PFS in terms of success rate. And then we further combine the PFS array in a parallel framework. We can further improve the performance to generate the motion plan with higher success rate. And in the right, we look at the figure that we show that which method actually finishes faster. So in blue part, we shows that PFS finishes faster, and green parts means RA finishes faster, and the red parts are all the timeout trials. And we see that even with a small size of RA, it improves the performance a lot. And as the library size grows, RA starts to generate more solutions faster than PFS. However, as we make the library size larger and larger, the performance starts to saturate because it becomes much harder and harder for the RA to find a promising motion plan to start from to locally optimize it to make a feasible solution. So the performance here saturates, and also here you can see it saturates to make it better. So it's also important to limit the size of the library in order to achieve a better performance. And finally, we showed a physics simulations where we play in gazebo, and to show the resulting trajectory is feasible in physics simulation. And here we use purely position controlled and running the joint trajectories. And we model the context to be a little bit elastic to make the derivative behave better, and also to give it some room to making the contact. And here it walks up to a staircase with hand contact to help it balance. And this is completely open loop with only joint level control. And so with those contacts, actually makes it very stable and not easy to fall with the hand contacts. And here we see it walks over a robot-like environment, and again using hand contact to help with the balance. And as you can see, we speed up is at 6 times, and it's mainly because we have to be making this very, very static, so which means it makes it walk very slowly. And finally can reach the goal in the end. Cool. So yeah, in the next section, we would like to discuss how we can estimate traversability of each region and in a larger environment to help find a contact sequence efficiently. So in previous sections, we introduced the PFS and RA, which can plan contact sequences in unstructured environment. However, in a large environment, the planner may have multiple selection paths. And if you run the contact planner without a proper guidance, it may choose the shortest path and potentially get stuck if the shortest path happens to be difficult to traverse. And therefore, we would like to use traversability, and which means an indicator of how easily the planner can find a solution in each region, and as a high-level guiding path planner. And the planner then generate paths to guide the search of contact planner in order to reduce planning time. And this idea of planning with a traversability is actually not a very new idea. So there are multiple approaches working on in different in a similar sense. So one major approach is to define cost functions based on the terrain geometries, such as change in height or terrain roughness, and use this cost function to search for paths to avoid undesired terrain geometries. And there are also approaches based on the appearance of terrains or objects and assign each region with a label. And the planner then acts based on the semantic label. For example, in the example we show in the bottom right figure here, a Mars rover takes images from of a landscape on the Mars and classify terrain types in each part of its view, as you can see here. And with the semantic classification, the Mars rover can avoid regions of certain terrain types, such as the large rocks region. And in our approach, we estimate traversability by directly predicting how well the planner performs in each region. Since we are planning in a large environment, we are interested in estimating the traversability of each region in the whole big environment. So for a large environment, we mean that the environment will have multiple selection of paths from start to goal. As you can see in example here, from start to goal, you have 2 paths to goal. And we'd like to use the traversability estimate to guide the planner to search regions, which is easier to find contact sequences so that it can speed up the planning. Furthermore, since hand contacts are not always available and not always advantageous, for example, if you're walking over a flat ground, you may not even need a hand contact. And we would like the planner to also decide which setup manufacturer to use in each region. And we call the setup manufacturer to use in each region as the motion mode. And here we show 4 motion modes defined in this work, including only use feet, and using feet with the left or right palm or hand contact. And also one final one is using all 4 effectors. And in the previous section, actually, we discussed using RA to help find contact sequences in challenging environments. However, RA requires computational overhead to match motion plans. As you see before in the video, we have to try multiple motion plans before we actually dig into one and see if it actually can work. And that we may need to optimize multiple trajectories before finding a fitting one. So in regions with high traversability, where contact spaces are very rich, PFS can actually be faster than RA. And therefore, to achieve max efficiency, we would like to combine the 2 methods by using PFS in easy regions and using RA in difficult regions based on the traversability estimates. And in this section, we are trying to use only one method in each region, and we assume that only one approach can be used in each region. Cool. So let's move on to see the framework of the planner. So given the start and goal and the robot model, as we said before, and we will first generate the guiding path, specifying where the robot should go through in a large environment, and which motion mode to use. For example, as you can see in the figure here, the guiding path informs the robot to go through the left corridor, and also to use the different motion mode along its path. Okay, and we then segment the guiding path based on its traversability, and assign difficult segment to use retrieve adapt or RA, and easy segment to use planning from scratch or PFS. And finally, we generate the contact sequences around each guiding path segment, and then connect them to form a final solution. And in order to inform the contact planner which path to take, we will need a way to inform the guiding path planners the traversability of each region. And in the following slides, I will focus on how we generate the guiding path. In particular, I will first talk about how we define and predict traversability, and then how we include traversability into guiding path planning to generate the guiding path. Finally, briefly talk about how the guiding path segmentation is done. Okay, so to evaluate the traversability, the most straightforward way is to run PFS and evaluate its performance in each region. And given any arbitrary pose where the robot roughly is in the environment, we denote this pose as PT here, as E2 pose. We would like to compute the traversability to move the robot with a transition specified by a 2D translation V using motion mode N. And to do so, we will first sample a set of footstep combinations centered around PT, and then directly run PFS from these sampled starting footstep combinations using a specified motion mode N to move a robot from PT to PT plus V. And finally, we will count the number of successful trials and define it as traversability. So traversability actually directly measures how well PFS can perform around each neighborhood of the region. And however, as you can imagine, computing traversability in this way would be prohibitively long to use in planning. Therefore, we would like to estimate it using supervised learning. So we train models to predict traversability using the contact projection clearance feature. And its idea is straightforward. With a given discrete contact transition model, we can find all possible contact projections for each pair of torso pose transition V and motion mode M, as shown in the figure in the right here. And for each contact projection, we check the distance of the contact away from the closest obstacle or the closest boundary of that surface to get a clearance score. And we then basically sum up the clearance score for the foot projections and also each hand projection to form the feature vector. And finally, we train support vector regressor to predict traversability, which is the number of successful trials of PFS in that region, based on the contact projection clearance feature for each torso pose transition and motion mode pair. And finally, we define the traversability cost to favor transitions with higher traversability. So it's a minus exponential function, but with a higher traversability, have a lower cost. And then we will use this traversability cost delta GTR to plan guiding path considering traversability. So to achieve this, we set up the guiding path planning in a simplified SE2 torso pose grid of the environment. As you can see in the right figure here, so in the environment, it's being discretized into SE2 grid, and we will plan a guiding path on the torso pose grid, and the path will guide the search in the later contact planner. And we'll use A-star to do this. And in the guiding path planning, the edge cost includes, of course, the traveling distance of the torso pose, and also a fixed step cost for each action. And most importantly, the traversability cost to tell the contact planner which region is easier to traverse, as we can show in yellow here. And also which motion, and each traversability cost will also include which motion mode to use associated with that cost. And finally, we add a motion mode changing cost to prevent the frequent switching of motion modes along the guiding path. And with this approach, the guiding path and the motion modes are actually decided in a single guiding path planning. So after this planning, we will know which path to follow and which motion mode to use. And after we get the guiding path, we will further segment the path based on its traversability to use PFS to solve easy segments and RA to solve difficult segments. And each segment should correspond to a motion mode and planning approach, either using PFS or RA. And to achieve this, we first segment the path at where the motion mode changes. And then we further decompose each segment with the aim to group the torso pose transitions with similar traversability costs together. So difficult difficult transitions grouped together, and easy transitions grouped together. And finally, we set up a threshold of traversability costs determined to use PFS and RA in each segment. And we basically use the mean of the traversability cost along that segment, and to see if actually is above the threshold or not. If it's above the threshold, we will use RA, otherwise we use PFS. And in experiment, we test in these two large environments. One is we call it two-corridor environment. As you can see before, this environment will have the two paths to going from the start side to the end side of the different rooms. And one is a two-staircase environment, which we change the height between these two big rooms in order to show that our approach does not necessarily have to plan an environment with a limited height change. It can plan with an environment with a significant height difference. And each small patch of area will have a 50-50% chance to be either a flat surface, like you see here, or a rubble field. And the planning time limit we said is 500 seconds. And if we can find a contact sequence within the limit, it counts as a successful trial. Here we show the number of successful trials among different test environments and among different approaches. So in the left, we show that in a two-corridor environment, using segmentation, specifying the multiple motion mode, outperforms original PFS planner, and also the PFS planner with only using segmentation. And our framework, including RA, actually improves the success rate, as you can see in the trend here. And we can also see a similar trend in the two-staircase environment, but the improvement is not as significant as in the two-corridor case. And here we show, my computer just froze a little bit. Okay, here we demonstrate the planning time of the proposed framework in an example two-corridor environment compared to the two baselines. And from left to right is using only PFS, using PFS plus segmentation and our framework. And our framework, including RA, actually can finish the planning much faster than the other two baselines. As we can see here, this one is going to be timeout in the end. Okay. And then we will move on to demonstrate our approach in a real robot experiment. So here we show a dual-arm mobile manipulator. Robot operates in a disaster site setting, and where it moves on a steep ramp. And you may treat the ramp as like a falling ceiling in the in a disaster site. So use your imagination, please. Yeah. And the robot keeps balance by making contacts on the tilted and cracked wall with a window in the middle. So you can see there's a window and a cracked wall surrounding the window. And the robot will tip over if it does not make the hand contact, just to let you know. And it is commanded to move the contact to the goal region from the original starting point to the goal region here. Okay. And we would like to test how traversability can help the planner to find a solution faster. It froze again. Okay, so in this video, we demonstrate the robot's motion in execution. While it is moving, let me explain the planning behind the scene. So there is a window in the middle of the wall here, and the robot has to either move above or under the window to reach the goal in the left of the window here. Here you can imagine that if the two end effectors is just like the 2 feet of a human robot, and the wall is like the ground used in the previous contact planning problems. And we train models to estimate traversability of the mobile manipulator and test to see how traversability can help the planner to find a solution faster, even in a smaller and simpler environment like this. So the goal region is said to be slightly higher than the starting contact poses are. So a distance-based heuristic will guide the robot to go above the window to do this way, okay? And however, the heuristic is agnostic to the reduced contact space caused by the pipe shown here. And search in that direction will actually be rejected heavily because it cannot reach too far away to go to the other side of the pipe. On the other hand, the traversability-based heuristic, which we propose, will guide the robot to go under the window and find the solution much faster. And the planner using traversability heuristic actually find a solution in about 0.11 seconds, while the baseline will take about like 3.5 seconds. And now it is close to its goal. And this robot is actually purely position control. So we actually add some kind of a soft padding in order to protect the robot. So we managed to finish this experiment before it breaks. That's a good news. So yeah, it reaches a goal. Great. So yeah, let's move on to our second half of the presentation, which we will talk more about how are we going to using learning approach to generate robust contact sequences considering robot dynamics. And as you can see before in our previous sections, including our works and also other conventional works, most multi-contact contact planners assume quasi-static balances to reduce the computation loads. However, this assumption is actually too conservative. For example, in these two examples we show in the bottom right here, the robot is going down a steep slope and also the robot is crossing a wide gap. It has to use dynamic motions in order to do in order to navigate in such an environment. And however, if you use a conventional quasi-static contact planner, it will fail to generate a solution in either of those cases. And furthermore, in case which quasi-static solution actually exists, the quasi-static balance constraint can still cause unnecessary rejection because it's over-conservative and can prolong the planning time. So the key idea here in this section is to swap the over-conservative quasi-static balance check with the dynamic feasibility check. And by relaxing the balance criterion, we expect the contact planner to more easily find a feasible solution. We also would like to add a dynamic cost to the edge cost of the PFS to generate dynamically robust contact sequences. And the robot dynamics can be computed using a dynamics optimizer. However, in that way, each new edge in the PFS will need to call this optimizer and takes about 10 to 100 milliseconds to compute. And it will be computationally prohibitive to do so. Therefore, we would like to use neural networks to predict the result of the dynamics optimizer and speed up the process. So before our work, the state-of-the-art approach to consider motion dynamics in contact planning is to formulate the problem as a whole mixed integer quadratic programming problem. They take a set of convex contact regions as a discrete decision variables I can see here, and also each of these rectangles are kind of a convex discrete regions, and incorporate all the dynamic constraints in the QP to solve the contact sequence and the dynamics profile in one problem. However, this approach scales very poorly with the number of contacts in the contact sequence and the number of convex contact regions. So it can only be applied to planning with short horizon, like 2 or 3 steps, in order to make it practical. So before we moving on to how we're going to incorporate the result and optimizer into contact planning, I would like to give a brief background on centroidal dynamics optimization. If we assume the robot has enough torque to generate the contact ranges, the robot dynamics can actually be ignored. The robot dynamics can actually ignore the joint torques and only consider what we call centroidal dynamics. And what actually means is that the derivative of the centroidal linear and angular momentum are determined by the contact range. The robot is acting on the environment, and also the gravity acting on the robot. So the centroidal dynamics can serve as a constraint in the optimizer, and we can then compute dynamically robust motions by minimizing a cost function, which is the weighted sum of the square norm of a linear angular momentum and also the contact ranges, and in a nonlinear program, and over a discrete time sequence with specified contact poses. Those are pre-specified. The contact poses and also time step are pre-specified. And for each contact transition, if the optimizer can return a solution, and we say the contact transition is dynamically feasible. And also, we would like to include this optimized objective value in the edge cost of a PFS planner in order to generate dynamically robust contact sequence. So in summary, to modify the PFS planner to consider centroidal dynamics, we add the dynamics cost in the edge cost of PFS where we show here. The dynamics cost C dyne is the optimized objective value of the dynamics optimization for each contact transition. And each state in the PFS now not only contains the contact poses, or you call it stances, but also tracks the COM positions and velocities in order to track the dynamics behavior of the robot. So we will also swap the balance check with a dynamic feasibility check instead of using a quasi-static balance check, which is quite straightforward. We add a new cost, and also we change the definition of a state. Finally, we update the constraint checker. In order to speed up, we are going to train neural networks to predict the result of the optimizer. So given a contact transition, we will have the input of initial contact poses where the robot starts from before the contact transition, and also initial COM, center of mass, or called COM, position and velocity, and also a newly made contact pose after the contact transition. And we first train a classifier to predict if the optimizer has a solution or not, which means if the contact transition is dynamically feasible or not. And it's going to be a binary classifier. And also we train a regressor to predict the dynamic evolution of the robot after the contact transition. So it will predict the final center of mass position and final center of mass velocity after the contact transition. And also it will also predict the dynamics cost, which is the optimized objective of that optimization. And we will train separate neural networks for contact transitions with different n effector involved. And each forward pass of the network will take about 0.1 millisecond, which is like 2 to 3 orders of magnitude faster than the dynamics optimization. So in experiment, we would like to test in 4 environments. In addition to the 2 environments we showed before, We also want to test with rubble environments with just a rubble field and also a rubble corridor where we can make hand contact with. We will allow like 30 seconds for the ANS stars to improve its solution. And since ANS star will produce a set of solution, we will finally check with a dynamics optimizer to see if the best solution is feasible or not. If it's feasible, we return that solution. If not, we will optimize the second best one until we find a feasible solution. So we first compare our approach with a mixed integer contact planner. So as we can see that we compare with mixed integer planner in a rubble field environment with about like a 14 contact surface in the environment. And we compare the time the time needed to find a feasible solution in each approach. And the proposed approach can find a feasible or kind of first solutions within a 0.1 second. And however, with a mixed integer planner, it will take 30 to 80 seconds, depending on how many contacts you use. So it's very slow. And also the user has to specify a number of contacts involved in this planning, which is not a trivial task for unstructured environment. And then we compare our approach with a quasi-static contact planner in a rubble field and rubble corridor environment. And here we show that the proposed approach has a higher success rate, as you can see in this column. This is mainly because the proposed dynamic feasibility check is a more relaxed constraint, and it can more easily find the solutions in challenging environments like this. And finally, we then run dynamics optimizations on the planned contact sequence and find that the resulting contact sequence produced by our approach also has a lower objective value as we show here. So the output contact sequence returned by our solution is more preferable in the sense of the dynamics optimization. So we are going to show two examples where we do the planning and execution on. And here we first show the wide gap test environment. The robot should find a first solution within 0.03 seconds, but we allow it 30 seconds to improve. Actually, doesn't need that time to do such thing. And the red trajectory is the predicted COM trajectory, and the blue one is the final trajectory of the dynamics optimizer. So they are pretty similar. And here we show a motion after the kinematics optimizer is run. And then we show another more challenging environment, the rubble corridor environment. Again, we run a planner and find a solution within about 2.5 seconds. And then we allow some time to improve the solutions. And then it finds the best solution in about 8.6 seconds. And again, the red trajectory is the predicted COM trajectory. And blue one is the final real COM trajectory after we run the dynamics optimization given the contact poses. And then we will basically run the kinematic solver. I didn't tune this very well. It's a little bit jerky in motion, but you get an idea about the robot is trying to move forward while using hand contact to reach the outside of the corridor. Okay, so let's jump here. So now we're moving on to our the most recent work about considering external disturbances in contact planning. So previously we have discussed about like how we can use neural networks to predict dynamic feasibility of a contact transition. And by including the objective value in the cost function, the planner will try to generate a contact sequence with lower momentum and ranges applied to the environment. However, it does not consider its robustness to the external disturbances. And although there are approaches showing strategies to recover a robot by making new contacts, we believe that the robot will need a high-level contact planner in order to get access to these contacts in order to capture a robot prevent from falling. For example, in the figure we can see here that the robot is trying to walk over a rubble field, and suddenly it's pushed toward the wall. And if the contact planner does not expect and reason such disturbance in the environment, it may just let the robot walk straight and have a shorter path length, and cannot access to the contact on the wall to save it back from falling. Therefore, we would like to develop a contact planner which takes potential external disturbances into account. And in this case, we can take a detour to walk closer to the wall and brace itself under the disturbance. And in this section, to simplify the problem, we only consider planning on foot contact in the contact planning. However, we will consider hand contacts for capture motions. And with this idea, we will need to check if the robot can stop itself under a disturbance, given the existing contacts and a newly made contact. And unfortunately, currently, there's no analytical tool to achieve this. So therefore, we'd like to follow our previous approach and to predict the result of an optimizer with neural networks and include its result in PFS. So what we do here is very similar to in our previous section. So just the difference is in the input and output side of the network structure. So the network will predict if given the input of initial contact pulses and initial COM positions, and also a post-disturbance COM velocity, and the newly made contact pulse. The network is going to predict if the robot can capture it or not. And here, we will model the disturbance as an instant change in the COM velocity. And we will verify with a Keynote dynamic optimizer to test if we can find a solution or not. And the difference here from the previous section is that we consider not only the dynamic side, but also the kinematic side, because we need to consider torque limit. Since this becomes a very essential constraint in determining capturability, if you do not consider the torque limit, the robot can basically capture everything with a sideway contact and basically capture every sideway push with a sideway contact because it can generate arbitrary force to reject it. So right now we also consider the torque limit. And to consider torque limit, we will need to consider the kinematics of the motion. And therefore, we run inverse kinematics with a sequential quadratic program in a loop of the dynamics optimizer. We run them basically iteratively back and forth to converge to a solution. And since we only consider foot contact in contact planning, and the capture motion will start from one existing foot contact, and we train separate networks for capture motions involving each different end effector. So in the contact planning, we will first specify a set of potential disturbances in each region in the environment, so that we will trying to we're trying to make the robot generate contact sequences that it can capture those predefined potential disturbances in the environment. So for each edge, one contact transition from state S to S prime, the probability that the robot can successfully finish the contact transition is the sum of the probability that the robot can reject each disturbance with the capture motion times the happening probability of a disturbance. So it's the successfully rejection probability times the happening probability of that specific disturbance. And to calculate the disturbance rejection probability, one straightforward approach is to just test a set of sample COM states along the contact transitions and take its probability product as a result. However, it's very expensive to do so. Therefore, we also experiment with only testing the first time step along the contact transition, shown in red here, and then we will use this, and then we find that the result is comparable in both approaches. So we will use this approach in the presentation. So to test if a robot can capture itself given a disturbance, we sample a set of potential capture poses based on existing contact pose, as shown in the bottom right here. So given a standing foot, we can sample a bunch of possible foot capture poses and a bunch of hand or palm capture poses. And we then check with optimizer or the network with these capture poses to see if any of them can capture the robot. If yes, the disturbance rejection probability is 1, otherwise it's 0. However, to increase the solution robustness to prediction errors of the network, in practice, we actually approximate disturbance rejection probability with this exponential function. So the idea is very straightforward, is that the robot is more likely to capture itself if more contacts, the NC here, is being predicted to be able to capture the robot. So it allows us to make the solution more robust to the prediction error of the networks. Okay, cool. So finally, we will set up a PFS to include the capturability cost as similar to what we did before for the dynamic cost. We add a cost C cap here in addition to the traveling distance cost and the fixed step cost. And we designed the capturability cost to be the negative log likelihood of contact transitions in successful probability, as you can see in the equation here. And in practice, we will let the weight of the capturability costs to be much higher than the other costs, so that by running A star, we will minimize the sum of negative log likelihood of the contact transitions, which is equivalent to maximize the total path success probability. And we will show this by showing an example here. So here is like a path with 3 edges from S1 to S4 states. And if the success probability of each edge is 0.99, and we can get a total sum of the path cost with this number. And however, if one of them drops to 0.5, which is a pretty bad edge, we shouldn't do that. And you can see that the negative log likelihood cost will significantly increase from the original cost and make this path to be undesirable one. And the robot will try to select the path that actually maximizes the total path success probability in this way. Great. So with these settings, we can generate dynamically feasible and contact sequence which is robust to external disturbances. And we would like to show them in this experiment. We'll test in 4 scenarios. And the first one is a very straightforward one. The robot is walking on a very narrow flat ground, a flat corridor, and with disturbances in 2 sides. And this robot will try to just walk there while trying rejecting the sideway disturbance. And the second one is walking over a rubble and with the wall in each side, while its potential push is from the other side to the wall. And here we show we call it oil platform environment, where the robot is trying to walk in a very big environment and with a strong wind blowing in different directions. And the structure in the middle is going to block the wind in each cases with a different region. And here we want to show that the robot will change its behavior if a disturbance in the environment is changing. So in the result here, we can see that in the first narrow corridor environment, the robot do something that's very straightforward and easy to understand. It basically spread its step width in order to make it to be more sustainable to the disturbance from the side directions. And the second one actually walks closer to the wall and to get access to the hand contact on the wall to reject the disturbance pushing it toward the wall. And in the final 2 tests, we show that the proposed approach can actually plan to go through this shaded region and to reduce its rate, to reduce its probability to falling down. And while the baseline will simply just follow a shortest path and can easily get blown away by this wind when it's walking around this region. And here in the final case, both of them show a similar path to take, so they also have a similar performance. And we compare them with the total path success probability, and we can see that the proposed approach achieves a much higher number than the baseline approach, which only considers distance. So here we finally we were going to show a experiment environment for the rubble with wall environment, where the robot will do the planning, and the left is the baseline, and the 2 right are they are all the proposed approach. So they can find a solution walking closer to the wall, while the baseline just walks straight forward. And then we were going to show when you get pushed with the baseline trajectory, it will get pushed and does not have access to a wall and just falls down in this case. Cannot find a solution to capture a robot. And where in our cases, the robot is walking closer to the wall, so actually can capture itself with the hand contact on the wall and to remain in balance after the push. Okay, so yeah, finally, to conclude the presentation, I have presented our work in addressing the challenges in multi-contact humanoid contact planning problems. And I introduced 2 lines of research. In the first half of presentation, I proposed the learning approach to use traversability to find easier path to follow. and use either PFS or RA to address regions that is difficult or easy to reduce planning time. And in the second half of the presentation, I show the use of neural networks to predict the result of dynamics optimizers and generate robust context sequences efficiently. And for future works, there are many directions we can extend toward. The first is that our planner assumes the environment is known and does not consider sensing and motion errors. And it would be nice to include that and to take that into consideration. And we may model the motion errors in the content planner and then deal with sensing errors using replanning approaches. And the second possible direction is to integrate the method with the gated locomotion approaches. In this work, we are dealing with an unstructured environment where the humanoid robot will need to carefully plan its contact in order to remain balanced. It is similar to what a human would do when climbing a mountain. However, when walking on more structured terrains, such as like walking on a flat ground, gated locomotion will work very well, and it's a more reasonable choice, just as we humans do. We do not plan contact when walking on flat ground. And therefore, I think in a greater sense of a locomotion functionality of a robot, a gated motion can always serve as a first guess of a solution. And then after we evaluate the gated locomotion solution may not be feasible in this kind of a typical environment, we may be able to switch to the content planner and to deal with this more difficult situation. And finally, in the part we predict the robot dynamics with neural networks, we have specific representations tied to inputs and outputs of the optimizer. And we predict dynamics based on entirely on the model used in the optimizer. And therefore, our whole performance is tied to how the optimizer can do. So it will be interesting to use the data-driven approach to identify more higher level stuff, for example, to identify objectives, or also the constraints from the task level, goals and constraints, and such as like social behaviors. And now we can then decide context sequences based on a more generalized objective. That's just like a 3 very big and broad direction to go. Finally, I would like to thank the committee and all the audiences joining my defense, and also thank my family, Dimitri, my lab mates, and all the collaborators, the robots, and whoever helped me in the journey of my PhD study. Thank you very much.